Good morning, we are Group 40, and today we present our CA6003 assignment. In this project, our business goal is to predict whether a diabetic patient will be readmitted within 30 days after discharge, where the target is 1 if the label is under 30. This matters because early remission is costly. It reflects care quality, and a good predictor can enable targeted interventions. For example, follow-up cares can care for high-risk patients. The core challenge is that healthcare data is messy. We face missing values, high cardinality, medical codes, and a severely imbalanced target. So our key question becomes, can strong data governance turn these data issues into useful signals and improve real-world model value? This slide summarizes our dataset. We use clinical records from 130 US hospitals from 1999 to 2008 with 100,000 encounters. The target is highly imbalanced. Only about 11.2% are readmitted within 30 days, so accuracy can be misleading. That's why we focus on ROC, AUC, RECORE, and F1. Our data audit also showed the key governance challenges: very high busyness like weight and payer code, and high cardinality ICD-9 diagnosis code with 800 unique values. This motivates our governance strategy next.
On this slide, we demonstrate that missing value governance can produce measurable gains even when the algorithm is held constant. In this diabetes readmission dataset, key fields such as weight, payer code, and medical specialty are heavily missing, and a common shortcut is to drop them, often removing clinically and operationally meaningful signal. To test the value of governance, we run a controlled experiment. We keep the same model, train, test split, and random seed, and change only the pre-processing strategy. Our governed approach uses two-channel encoding, has XXX indicator plus an explicit missing category. We expect improved recall while preserving interpretability. Here, we addresses a practical modeling issue. Medical specialty contains many sparse categories, which can cause one hot encoding to explode in dimensionality, increasing sparsity, training cost, and overfitting risk. Our solution is frequency-based grouping. We keep the top 10 most common specialties to preserve signal, and we explicitly retain the missing category as a governance requirement. Every remaining specialty is mapped into a single bucket, other specialty. The result is a low cardinality feature, medical specialty grouped, and that reduces dummy variables, improves model stability and generalization, and keeps interpretation straightforward. Top specialties versus other versus missing. This slide addresses outliers in key utilization variables, such as time in hospital, number of lab procedures, and the number of medications. Extreme values can dominate the learning signal, skew feature distributions, and make model training less stable. We first screen these variables with box plots to confirm heavy tails and potential extremes. Our governance choice is robust clipping rather than dropping records. We kept values at the 5th and 95th percentiles, similar to winsorization. So we reduce leverage from extremes while keeping the full sample. The expected effect is more stable optimization, better generalization, and future values that stays within realistic interpretable ranges. This slide shows how we confirm the raw ICD-9 diagnosis codes into model-ready clinical features. The original DAG1, DAG2, and DAG3 fields contained hundreds of discrete ICD-9 codes, so naive one-hot encoding would generate over 2,000 sparse variables, increasing overfitting risk and making simpler models harder to train. To address this, we implement a rule-based mapping function aligned the clinical classification scheme proposed by ZHAO 2014, collapsing codes into a small set of minimal categories such as circulatory, respiratory, digestive, diabetes, and injury. We also handle VE codes as other and missing values explicit. The result is low dimensionality and clearer interpretability.
Now, we move to the algorithm design. Our goal here isn't just to build a model, but to conduct a scientific experiment to prove the value of data governance. We design a rigorous A and B test. On the left, we simulate a lazy analyst workflow, taking raw data and simply deleting difficult columns. On the right is our governance workflow, utilizing all the engineered features we built in part 2. Most importantly, To ensure a fair comparison, we kept the machine learning algorithm constant. We use the exact same logistic regression with the same random seed for both pipelines. This ensures that any performance difference we see later is strictly due to data quality, not model tuning. Let's look at the specific differences in the data input. This corresponds directly to our feature engineering code. First, the baseline drops the diagonalized column because 800 unique codes are too complex to handle directly. Our governance model, however, maps this to 9 clinical growths, preserving critical medical history without noise. Second, instead of deleting columns with missing values like weight, we engineered flags. As we saw earlier, missingness is a behavior signal. Finally, we applied log transformation to scoot numeric features. This is a critical step for linear models that the lazy baseline gives a digestible depth of information versus raw noise. For model selection, we adhere to the assignment requirement for basic interpretable models. We chose logistic regression as our primary engine. In healthcare, a black box is dangerous. We need to explain why a patient is at risk via coefficient. However, we added a unique twist to demonstrate novelty. We ran a linear regression benchmark. This is unconventional for classification, but it serves as a robustness check. If a simple linear line fits our data well, it proves that our feature engineering, like log transforms and grouping, successfully simplified the complex biological relationships. We also use the class weight equal to balance to ensure the model doesn't ignore the minority class of readmitted patients. Finally, we define what success looks like. With only 11% remissions, accuracy is a trip. A model could be 89% accurate by simply saying everyone is healthy, but that would be useless. Therefore, we prioritize recall above all else. In our design, a win is not achieving the highest accuracy score, but identifying more high-risk patients, reducing false negatives. This strategic choice directly sets the stage for our results section, where we will see how the governance model traded a tiny bit of precision for a significant gain in safety.
Okay, this part is about the model evaluation and the performance, and this slide is talking about the results. Let's look at the results. You might notice the AUC dropped slightly by 0.31%. This is expected because when we grouped 800 diagnoses and codes into 9, we lost some fine-grained detail. However, look at the recall, look at the confusion matrix, and it increased by 0.46% in a hospital setting. Recall is the safety metric. It measures how many sick patients we correctly identified. A higher recall means we are catching high-risk patients that the baseline model missed. We effectively traded a tiny bit of mathematical precision for greater patient safety. To validate our feature engineering, we run a robust check using a simple linear regression. Surprisingly, this basic linear model performed almost as well as the logistic regression. This proves that our data governance strategies like log transformation and grouping successfully made complex medical data linear and easy to model. It confirms that the predictive power comes from our clean data, not from using a black box algorithm. And this slide represents the true value of data governance. Unlike the black box baseline, our model explains why patient is at risk. First, look at the red bars. A prior inpatient visit is the longest predictor. History repeats itself. Second, look at blue bar for HbA1c measured. It has a negative coefficient, meaning it reduces risk. This proves our hypothesis. The simple act of testing a patient is a proxy for high quality care. And this level of insight was impossible with the raw data. This is what doctors need to make decisions.
This slide gives us conclusions. With the same model, the claim pipeline shows a trade-off. AUC drops slightly, but recall improves. AUC decreased because grouping over 800 ICD-9 codes into 9 clinical groups reduced detail. Recall improves because we catch more true high-risk patients, and in high scale, missing them is costly. With added signal like head weight and HbA1c measured, the claim model is more interpretable and robust, so it's our preferred deployment. In our last slide, we summarize implications, limitations, and next steps. For imbalanced healthcare tests, we prioritize recall and AUC over accuracy. More importantly, data governance decisions are model decisions. Missing value handling affects signal versus noise, and feature cardinalities affect stability and compute cost. For deployment readiness, logistic regression improves clinical transparency, and the governance pipeline support auditability, traceability, and reproducibility. On limitations, we mainly test ALR. Pharmacist was not audited, and there may be temporal and cross-hospital shift from 1999 to 2000. Finally, as next steps, we plan stronger calibrated models, subgroup fairness mitigation, and richer clinical features like comorbidities and longitudinal history.